Hello, everybody. Welcome to everybody who's coming to class. Quiz is hopefully up. And you can get in there. It's a 6-minute quiz today. Welcome to class, everyone. If you're just coming in, quiz is underway, 6 minutes. Are you guys all getting your COVID shots now? Good. It won't be long and we'll be able to safely get together. That'll be nice. I've had both of mine. Back in Monday, it's 2 weeks since I had the second Pfizer shot, so. I want to remind everybody that we are going to drop the low 5 grades of the quiz. Get a lot of quizzes, but we'll give you a little bit of latitude. Okay, if you're just coming in, quiz is ongoing. 6 minutes, so we'll stop it in 5. Yeah, this is a little bit tougher quiz. Most people are in the 7 to 8 range, just so you guys know. If you're not doing too bad if you're in that range. I think only 4 people in the prior 2 classes got above an 8. Oops, oh, didn't mean to do that. Although I guess probably everybody who needs the password has it now. So I can move to that now. Okay, we'll wrap it up in just a second. Okay, welcome to class again. Thank you for coming. The wisdom of the day: controlling complexity is the essence of computer programming. This is really what today is all about. Okay, so we're going to be learning a new method for representing programming objects called classes. And really it's all about controlling complexity. And as I've said before in class, is complexity, we're not worried about complexity for the sake of the computer. The computer doesn't care about complexity, it turns out. What happens is we care about the complexity that's perceived by the humans, because if it gets too complicated, we can't figure it out. And if we can't figure it out, we can't make it work. And not only that, by the way, a big issue of complexity is security, right? These days, we're always worried about computer security and getting hacked. And recently it came out that over 500 million Facebook users' identities were exposed. Not good, right? Why? A lot of this has to do with complexity. And if we can somehow keep complexity down, we understand better what the vulnerabilities of our software is. We understand how to make it work. We understand how to make it work better. We understand how to change it and fix it. Now, Brian Carnigan was very important. He was one of the contributors to development of Unix back in the early 70s. And he, Unix changed the world, right? Chances are you're staring into the screen of a computer that's based on Unix, okay? And your phone is, and everything, almost everything has been impacted by Unix. And so Unix is huge. Now, so of course on April 13th, Lab 5 is due. I'm going to talk about that briefly to kind of get us up to date, and chapter 10 exercises. I want to review this. Lab submissions and late policy, which is on the web page, must be submitted on Moodle, right? It's not good enough just to submit it in the in REPL, and it's due by midnight 5% penalty for up to 12 hours late. One lab may be up to 24 hours late. The cutoff date, 12 hours after the due date, will be enforced for future labs. If you need extension more than once, you must talk to me, okay? Sometimes it's arrangeable, depends on the circumstances, but you have to come to me. If you can't come to me after the fact and say, it's been 3 days since it was due, but can I use more time? You need to come before that. Okay, today's agenda. We did quiz 18. We're not going to do a Pogel today. We're going to do something else that's going to be fun, I think. Of course, we have the history essay for the 2000s, and we're going to learn about abstraction in classes. I'm also going to talk about Lab 5 a bit. Who's willing to talk about the history of the 2000s? These are back when you were children.
I can, if.
Okay, thank you.
So I wrote about iTunes. And I thought this was really exciting because iTunes really did change the face of music distribution in the music industry. And so when I was researching it, it was released by Apple in 2001, but before that, it was developed by a man named Brian, I'm not sure, Kincaid or something. I'm not exactly sure how to pronounce his last name. But he developed it, and he had worked for Apple before, but left. And so he developed it with a partner and named it SoundJam MC or MP. And they released it, and then Apple caught wind of it and bought up the rights to it, and then brought them aboard, and they continued development of the code under Apple supervision, and they actually still work for Apple. But what I thought was really cool is like after it was released and after like the iTunes library was released, after less than a week, 1 million songs had already been downloaded by like the general public. I thought that was really cool because it was so telling of how the future of music distribution would turn out to be.
Right. Before then, of course, for the most part, if you wanted music, you had to go to the store and buy a CD or a cassette tape, or if you go back far enough, a record, right?
Yeah.
And I'm old enough that records were what I used when I was and cassette tapes. But yes, music distribution, and so people used to have their big cases, like bookcase-like things in their living rooms or whatever that were filled with all their music, and then they would pull it off the shelf and play it. And the whole idea of being able to just pull it off the web and put it on, an iPod and eventually an iPhone and other devices was pretty revolutionary. Anybody else want to talk about something? Nobody? Nothing interesting going on during that time?
I can share mine.
Yeah.
I picked The Sims because it's like an open world kind of game where you have so many choices you have to make, and like I'm sure when we think about like managing complexity, like I can't even, because all we kind of know would be like make functions with if-else statements in them, and like that's a lot of if-else statements. So I was just kind of wowed by like that exists.
So yeah, this whole thing, the whole idea of a virtual world, right, that was kind of the beginning of that. And there's been lots of things done in that area. And and there's been books written about it. And this whole idea that you can create a virtual world and somehow immerse yourself in it. Of course, with The Sims, you were just looking at a screen, but with virtual reality, perhaps of various sorts, you can actually go into a virtual world and kind of experience things like, could you perhaps, appear to be walking around the Louvre in France from your own, you know, living room, right? And kind of experience, right? Or completely whimsical worlds that are made up, right? So this whole concept of virtual worlds is very interesting, and you know, and leads to, in fact, a lot of conjecture. In fact, a lot of work has been done on the concept of, with enough computation, you can essentially recreate a replica of the world we live in down to the atomic level. And you know, there are scholars and sort of visionaries that believe that if there is such a thing as basically bringing people back from the dead, they believe that this can eventually be done when you have as much information as you do, when you have complete information, and when you completely can model and record everything that is happening in the universe, you can actually map backwards, and you can actually pluck people out of the past and recreate them with their memories, which is bizarre, right? But there's people who talk about this, and that you know, that in the future, what mankind will do is essentially they will use the resources of our universe to build more and more computation, to build these virtual worlds that we can go into and essentially live forever, right? This is sort of the dream. And so you know, anyway, and you know, there's lots written on this, you know, if you're interested more in that concept. Okay, so as we saw, we talked about complexity. Now we're going to talk about something called abstraction. This is a really important principle in software development, and it's actually a really important concept in general for humans, and understanding, and the philosophy of how the brain works even, right? How do we understand the world around us? How are we able to capture concepts when people talk about things and generalize and learn? How do we do all these things? Well, a lot of it has to do with abstraction. And so we're going to talk about abstraction for a bit with relation to computer science. Before I do that, though, actually, I'm getting a little bit ahead of myself. I want to talk a little bit about Lab 5. We've already talked about it some. Your goal for Lab 5 is to go through these series of steps that I'm giving you, and I'm not going to read through them here, but it's to go through and eventually find out what is the most popular word for each of the speeches. Now, Andrew pointed out that I made a mistake, and so I'm going to admit it. And remember the text for the president, I actually assembled this myself. These are all, turns out that John Quincy Adams apparently and John Adams are swapped. So I didn't get that right, so sorry. That's my disclaimer. There was a lot that went into pulling all this together for you guys. So I guess if that's the only error I made, it's not so bad. So anyway, so of course, what you're going to have to do, what I have is all these files out here. Now, rather than bring all these files into your program, what we're going to do is we're going to read them. And it turns out we're also going to read the stop words directly from the web. Because that's a worthwhile things to know, is that with Python, you can actually open up files that are not on your computer and are out there on the web. And in fact, you could actually go and open web pages up from Python, and you can scrape web pages. And what this means is you can actually mine the internet for information from a Python program using various modules that we're not going to talk about in this class, but it's good to know that if you're working on a research project, and you could actually make a project that goes out and pulls data directly from the web. So I wanted to show you how this works briefly. It's pretty simple. It turns out if you import requests, it allows you to talk to the web. And here I have two strings defined, stop URL, which is the URL for the stop file, right? This is exactly this is exactly the thing I went to. If I copy this and go over here and paste it, we see that's our stop words. That's just sitting on a server that I have on campus. And so I can open that up. What I can do is I can say, it's kind of like an open, I can say request.get stop URL, where stop URL is that URL to that file. And this is kind of like a file object then. And in fact, what it is it's just a big string is what it does. It reads that whole thing into a big string. In fact, I can prove that if I print out my file, we can see, oh, right, I have to turn it into text. It comes back as a response item, response 200. And we can see it's just a bunch of text, but it has the new lines in it. So what I can do is I can take that request item, I can turn it into text, I can split it by the new lines, and what I get is a list of all the words. So that's nice and easy, right? That's a nice, easy way to read a stop file list. I'm just turning it a stop file on the web and turning it into the list. Now, like I mentioned, this file contains the names of all of the speeches. Now, the thing is we can put that together with this https://cs.kenyon.edu/text/president. And what I can do is I can make a speech URL. And what I can do is I can make it the URL head plus, of course, we're going to read it out of this file, but I'm going to do it manually. Let's get Thomas Jefferson's first speech and put it in here. And then I can take this same code and I can read the speech URL. So I'm reading the speech. Instead of reading the stop list, I'm going to read the speech. And I'm going to break it into lines. And now if I run this, I should see that lines, well, it always helps if I print it out. We see that lines contains a list of all the lines in the speech. And then from there, I can take the lines and break them down into words, and then I can count the words, right? And so that's exactly what we're going to do. What you're going to have to do is write a loop. You're going to read in the speech names, and then you're going to go through the speech names one at a time, open up that speech, read in the speech, break it up into words, count all the unique words, then go through that list of unique words and find the one with the highest number. And then you can print out for each speech, which is the most common word in each speech and how many times it occurred. In George Washington's first speech, government was the most common. It showed up 8 times. Oath in his second only showed up 2 times, interestingly. Union in John Quincy Adams, 20 times. Government is popular, 12 times in Thomas Jefferson's first, right? So that's what we're doing with Lab 5, okay? So I have given you in Lab 5 a place to start with, but I'm not quite as, I'm being a little more hands-off in terms of, I'm giving you the functions to write. It's up to you to finish those functions and then to assemble a final program, okay? You need to use those functions. Don't start from scratch. Start from the code that I give you, finish those functions and build a solution. I've pretty much structured it all out for you. Any questions on the on Lab 5? So you're going to be using dictionaries. The stuff that I did last time directly is useful. You're going to be using dictionaries. You're going to be looking them up, putting them, so the code I gave you, you can reuse. Now, I want to mention one thing about reusing code. You can reuse code for any code that I show you, you can reuse. You cannot use code from the web. You cannot copy each other's codes. That includes, by the way, because this has come up, if you go to the MSSC or you come to my office hours and somebody is sharing their screen with the tutor or with me, you're not allowed to basically look at another person's code that's being shown and copy that, okay? That's a form of plagiarism. So don't do that, okay? Because I can tell when that happens. So, you know, write all your own code. But again, you can use my code and modify it. That's fine. But you can't use each other's code. You know, that leads to a visit to the Academic Infractions Board, which is not a happy thing. All right. Any questions? Okay, so we were talking about abstraction. Now, here's a nice little Picasso, right? He started with this bull and this bull, and he's making what we know of as abstract art, right? I guess he's going this way, and he ends up with his name. But, you know, so what's he doing? Well, you know, this still looks like a bull. He's abstracted away a lot of the details, but he still has a lot of the essence, right? Right, this, in a sense, this is a specific bull. This is sort of the idea of a bull. But for most people, you know, you kind of recognize that, right? So we want to understand the importance of reducing perceived complexity. We want to understand the concept of abstraction and modeling, and to learn the basics of class construction and use in Python. Now, let's take a little step back to try to understand this. What steps do you take when you want to make a phone call? Well, not very much, right? Typically these days, you pull your phone out. If you're not wearing a mask, it'll probably recognize your face and open up the phone, right? And then you maybe click on the phone thing and you click on the name of your friend. And in a few seconds, when you hold it up to your ear, you're talking to them, right? It's not very many steps. It's pretty simple. Now, what really happens when you make a cell phone call, right? Not what do you do, but what actually goes on? Well, it turns out we could spend your entire college education talking about what happens in the first few seconds of a telephone call, and we still wouldn't be done, okay? There's so much that goes on, right? You know, just some high level things that has to do. Your phone has to connect to a tower and it has to negotiate a connection. That could take us the rest of, you know, your school year just to talk about what goes on there. You know, the cell phone must authenticate. What does that mean? It has to prove who it is. It has to exchange keys. It has to set up encryption. It has to agree on frequencies. It has to negotiate power levels. Now, it turns out if the tower isn't owned by your carrier, there's all sorts of negotiation that has to go on behind the scenes so that the right people get paid for the services that you're using. Even if you just pay a single monthly fee, there's all sorts of transactions that are taking place every time you make a telephone call. A specific channel must be allocated, both a frequency and a slice within that frequency for the cell phone to communicate over. The phone must digitize an analog signal from your voice, convert it into a digital signal, then convert it back into an analog version of the digital signal that's encrypted, that it sends to the tower. Then the tower has to undo all that, turn it into bits of data, ship it over through all sorts of places, eventually to another cell phone tower where it repeats the whole thing and it goes down, right? And I could go on and on, right? This is really, right? So what's the point of all this? What's the point of telling you it's easy to make a phone call? It's actually hard for a phone call to be made, right? In fact, there's nobody on the planet who understands all the pieces that make a phone work. That's how complicated it is, right? There's nobody. Now I know a lot about what's going on in the phone. I know a lot about that because I'm a computer scientist and I work in digital communications is my area of expertise. And I'm telling you, cannot know all of it, right? There's so much that goes on that that no one person can master all of the technologies. And so what happens is lots of people work together and make lots of pieces and they put it together and they build not just a cell phone, but an entire infrastructure across the planet that makes cell phones work. In fact, I would argue that the cell phone system could possibly be the most complicated thing that humans have ever built, right? And really, at this point, when we're really talking about more than just the cell phone, because it turns out that the cell phone and the internet are pretty much unified. They're all using the same underlying technology and running over the same fiber optics. And this whole system of global communications, there's just nothing mankind has ever built that's as complicated, you know? But yet, if you have a 4-year-old brother or sister, they can pick up a phone and they can call their grandma, right? Isn't that remarkable? You know, and the world wasn't always this way, right? If you go back a couple hundred years, for one thing, the most complicated thing on the planet wasn't that complicated by today's standards, but anything that was complicated, you would never have a child use. They'd probably be killed, right? You certainly wouldn't have a child try to run a locomotive, right? And which was maybe one of the most complicated things, 300 years ago, or 200 or whenever they were around. So again, it has been said that practical CS is fundamentally about managing complexity. In fact, Dijkstra, again, he comes up a lot, says the art of programming is the art of organizing complexity and mastering multitude and avoiding its bastard chaos as effectively as possible. Always one for pithy sayings. Another one that's kind of interesting that I love is the competent programmer is fully aware of the strictly limited size of his own skull. Therefore, he approaches the programming task in full humility. And among other things, he avoids clever tricks like the plague. So the idea is we strive to make things simple because what we're trying to do is make things that our tiny little brains can understand, right? I mentioned a few weeks ago that no, what did I mention a few weeks ago? That I don't remember. I got a message on my phone and it completely distracted me. Sorry. Okay, thus our program is to manage complexity. It's not about reducing the actual complexity, right? It's about managing it in a way that different people or us at different times can look at different pieces and understand those little pieces, right? That's why I push you guys so hard to write functions to make your projects work, right? If you could do the project that was just due, project 4, without any functions, but it would be a nightmare. I wouldn't do it that way. It would be hard for me to understand. I could do it that way, but it wouldn't be smart, right? And so what we do is by breaking it down into these pieces, then we can take a piece and put it here and another piece and put it there, and it makes sense, right? And that's why I insist that you break your programs up into little pieces, right? And so if one of your pieces of your program has more than about 20 lines of code, and even if you're at 20, you've maybe lost control and you need to take a step back and make lots of little things, test them, and then put them together, okay? But what are some other ways we can manage complexity? Well, Another way we can do it is through something called models and abstraction, okay? So let's think about this for a moment. A cell phone is really a model of the act of communication, right? When we use a cell phone, we don't think about frequencies and digitizations and phase modulation and blah, 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 right? We push a button and we talk to somebody and the phone effectively disappears, right? We don't have to think about the phone, right? That's an example of, the best example of good technology is technology that becomes essentially transparent, right? Our tasks are the things we think about and not the item that allows us to do that task. So a steering wheel is an abstraction, it turns out, right? Because a steering wheel lets us control the direction of the vehicle. Now, we call it an abstraction because we just turn it to the right, the car goes right. We turn it to the left, the car goes left. You know, there's a lot going on underneath the hood of your car to make that happen. But I'm going to bet that most people in this class don't know what's between the steering wheel and the wheels, right? You just trust it to work. And in fact, when you're driving, you don't think about rack and pinion. You don't think about power steering boost. You think about, I want the car to go to the right, and so I'm going to move the steering wheel to the right. And so the steering wheel becomes an abstraction for direction. And a credit card is an abstraction for money, right? Basically, a credit card allows us to go through the complex task of removing money from an account out there in the cloud and moving it to another account that a company has that we're going to buy some product or service from. But we don't have to think about all that. We just push the card in, hit approve, and bang, we're done, right? Can you think of some other abstractions you use in everyday life? I mean, let me just prime the pump with a simple thing. Look over the wall of the room you're in. There's a wall, there's a light switch, right? You can just flip that on and off, and in your brain, you don't think about, I'm enabling electrons to flow, or I'm connecting 120 volt wires. You're thinking this switch turns on that light, right? It's an abstraction of enabling a light, right? How it works, most of us don't ever think about. Or the thermostat on your wall that controls the temperature in your house, right? We can go on and on with types of abstractions. So in programming is all about creating a simplified model of something we want to represent. This is what we do, much like Picasso was creating a model of a bull that was abstracted away from a lot of the details. The goal is to find a model that only has those features that we care about, right? So, and abstracts the features away, ignores the features we don't care about. For example, let's say you want to build a system that's going to keep track of students at Kenyon, right? That system isn't going to keep track of a person's blood pressure, probably. It's not going to keep track of the we don't keep track of people's heights. We don't keep track of how fast a person can run a mile. We don't keep track of, you know, we don't keep account of the individual hairs on your head. Now, that's all information about you, but we don't care about that, right? What we care about is what courses you're in, who your advisor is, what grades you got, how much you have, how many of your requirements you have met, and on, right? There's the things we care about and there's things we don't. And so Kenyon's perspective with respect to the information system that stores information about Kenyon students, we create a model of a student that is exactly the things that we care about, and we ignore all the things that we don't care about. That's abstraction. Now, it turns out that the ultimate extraction, a very simple mathematic, the Turing machine is a mathematical model. It's literally a set of equations that model the essence of all computation. And that's what Alan Turing invented. Given any computer algorithm, a Turing machine is capable of simulating or describing that algorithm. So that's an abstraction. And we use that abstraction, by the way, to prove a lot of the principles that are important to computer science. And so how does it work? Well, it's sort of like it creates a model of an infinite tape that you can store ones and zeros on, a read-write head, and a state. And you simply read things and write things. Sorry, I want to open it. You read things and, oh boy, I created a mess there. You read things and write things from the tape, and you go from state to state, and that's it. All right. Okay. So, hiding complexity in a programming language. How can a programming language like Python allow us to hide complexity? How does a programming language allow us to build models of appropriate abstractions of the parts of a problem we care about? Well, we use something called classes and objects. And we've already kind of seen these things, right? In a programming, a class is a model of something we wish to represent. It is the design of a model. So an object is an instance of a class. So we have a class, which is a model, and an object, which is a thing of that class. It's a realization. Think of it like an object is a blueprint. A class is a blueprint, and an object is like the house that you build from that blueprint, right? Consider something simple. What if we want to represent a bank account? What do we need to know about each bank account? What do we need to do to the bank accounts? So what do we need to know about a bank account? Can you guys think of some things? Anybody?
The PIN number?
Okay, so you better keep track of the PIN for an account. What else?
The name of the owner.
Yeah, you want to know who owns that account, right? So that's an important thing. What else do you want to know? Whoops.
The account number.
The account number. We probably want to know how much money's in the account, right? We probably want to have a list of all the transactions on that account. We want to know the interest rate, right? So these are things that we care about in an account. So let's talk about classes. So a class has two parts. When we talk about a class, it turns out it has what we call the interface and the implementation. The interface is the part that a person sees, and the implementation is the part that makes it work. Okay, so the interface to your car is a steering wheel, a brake, and a gas pedal, and maybe a gear shift, and there's a few other things, right? That doesn't make it work. That's what allows you to control it. That's the interface, right? The implementation of the car is largely underneath the hood or beneath the skin. There's motors and valves and servos and belts and pulleys and pistons, right? Those are the implementation, right? The implementation is largely hidden. The interface is what you see. So think about your phone. Your phone, what's the interface? The interface to your phone is what you see on the screen largely, right? There's also might be a few buttons. There's not very many buttons on a phone, but there's a few, right? Buttons and switches. And there's a jack where you can plug in the charger. Now, what does the inside of a phone look like? Well, it's got a bunch of crazy stuff. It's very complicated inside your phone, extremely complicated. In fact, I would say that there's more complexity in each of your phones than existed on the entire planet in the year 1950. If you took all of the things that man had ever built, technology-wise, and you had a way of sort of measuring the complexity, there's probably more complexity in a single cell phone, just inside one phone. There's an amazing amount in there. So the interface is seen by public, the implementation is hidden away, and in fact, sometimes it's even secret, right? Apple doesn't want you to know exactly how their phones work because they don't want you to steal their ideas. Unseen, private. Now, again, object and instances, and you can think of an iPhone, a particular model like an iPhone 12 is a class of things. You say, oh, I have an iPhone 12. Well, you know, lots of people have iPhone 12s, but there's only, you know, there's one concept of an iPhone 12, and everything is like, that's an iPhone 12 is like that concept, is like that design. So let's take an example and let's think a little bit more about the bank account. So when we got a bank account, remember, there's two aspects of a bank account that we want to think about. We want to think about the information that we store when we represent a bank account, and we want to think about actions or the things that we do to a bank account. So we want to think about the information and we want to think about the actions. So what is the information? Well, we want to know what type of account it is, perhaps savings, checking, mutual fund, something. We want to know who's the customer, who owns it, and we want to know how much is in there. There might be other things, right? There might be interest rates. There might be, we might need to keep track of the number of transactions because they might have a minimum or maximum number of transactions. That's all information that we store. And then the actions are the things that we do. What do we need to do with a bank account? Well, first and foremost, we have to be able to create it, right? So it turns out that anytime we have something, one of the major to-do things is to create that thing. We call it a constructor. So we want to be able to create it or construct a new one. We want to be able to put money into the bank account. We want to be able to take money out of the bank account. We want to be able to check its balance, right? Those are the major sorts of things we might want to do with an account. And there's a few other things, like maybe we want to close out accounts. Maybe we want to merge accounts. Maybe we want, but these are the main things that we want to talk about. So sometimes when we think about classes, we kind of use a diagram like this, right? And it's divided into three parts: the name of the class, the state, the variables. Remember, that's like here, information. What do we need to know about that class? It's the data. And then the interface, which is the things that we want to do to the class, right? Just like a steering wheel allows you to steer the car. That's an interface, right? A bank account allows you to deposit money. That's an interface. It allows you to withdraw money. That's an interface. It allows you to check your balance. That's an interface. We can think of these in terms of the name, the variables, and the operations. By the way, operations are basically like functions, right? We already know about functions, but the operations are methods. We call them methods instead of functions, but they're basically the same thing. The difference between a function and a method is a function can work on any data, and a method only works on a particular class. So it's kind of like a limited function, and so we call it a method. So let's think about the account class. Here we see up at the top, we have account. We see the data that we store, a name for a particular account. Every account, we need to know the name. We need to know with the account of the name of the account, the name of the customer who owns that account, and the balance. That's sometimes called the state or the variables, right? Any account has a certain state. You know, you might think of somebody saying, well, the state of my checking account is terrible, right? What are they saying? They're saying it doesn't have a high balance, right? Or you might say the state of my account is plum, because you have a lot of money in it. And then there's methods or operations, right? Two different ways of talking about it. It turns out in Python, we always have a special function called a init with 2 underlines before and 2 underlines after. That's a creator. Every object always has a creator, an init function to say, how do I build one? And then we want to be able to withdraw money. Whoops. And when we withdraw, we want to give it an amount because we have to say this is how much we want to withdraw. So that looks like a function, doesn't it? It's a name and a piece of data. Here is a deposit and how much we want to deposit. Now get balance is like a function that returns something, but we don't have to give it anything. And we might want to get the name of the account. So we could have a function called get name. Now, once we have defined the account class, we can make lots of instances of that. Like here's Bill Jacobs's checking account, and here's Amanda Blick's savings account, right? And we can make as many of these things as we want. So this is the class, this is the template, this is the blueprint, this is the cookie cutter. These are the objects, these are the cookies, or the thing that we actually make, okay? A class is like a design, an object is oftentimes called instances. We have different instances of the account class, just like we can have the concept of an iPhone 12, and we can have many instances of that iPhone 12 because lots of different people have them. So we can have lots and lots and lots of them. So again, let's see how we do this in Python. Now, and again, the whole idea here is when we define an object, we define these 3 things. We always define, when we define a class, we always define its name, we say what data is going to be in it, and we say what are the things we want to do with it. And so that thing, an account, is called an abstraction because what we've done is we've created something that represents what we care about when we think about a bank account. All right. So let's look at some actual code. Now, when we make a class, we usually make it in a different file, right? Most of the programs we've written before, in fact, all of them, are in a single file, but we're going to break this into 2 pieces. We've got our normal main.py, and here we have another file, and we're going to call it account.py. And notice over here at the top of main, I say from account, import account with a capital A. Now over here in account.py, I have the first line in there is class account object colon, and then we have some functions. Okay. Now over here, what this is saying is in this program, I want to be able to use this class. Now we've seen that before, haven't we? Because we've imported Turtle, we've imported math. For the next lab, we're importing, I forget what it was called now. We're importing whatever we're importing, results I think it is, which allow us to talk to the internet, right? And so what this is saying is from account lowercase, because the name of this function is lowercase. You don't have to put a P, a Y on the front, but this says this file.py import this particular class. You could actually have more than one class, and this is saying which one to get out. But usually we only have one class per file, so that's just the way we do it. So now, notice that, what do we have in here? Let's look in here for a second. In this function that says underscore underscore init underscore underscore, we have 3 parameters: self, name, customer, balance. So this is like a function, although it's actually a class method, but it works very much like a function, but it's a function just for this class. And in fact, this self is sort of a clue that there must be something different. Notice each one of these has a self. And the whole, now this is actually kind of wonky. Most languages require you to have some sort of self-referential thing when you're working with classes, but Python is alone in that you actually have to pretend like you're passing in a parameter, but then you don't actually pass it in, you don't actually use it. You actually do pass it in, but in a different way. I don't want that to be too confusing, but the whole point is self is a way of talking about a particular instance of an object. You're talking about yourself. So here we have a knit, and what a knit means is I want to create a new account. And when we want to create a new account, we need to give it a name. We need to give it a customer name. This is the account name, the customer name, and this is the balance. Now, we haven't really seen this before, but when we're defining a parameter in a function, if we say the name of the parameter and then we say equals a number, what we're saying is hey, they don't really have to include this parameter if they don't want to. And if they don't want to include it, then I'm just going to make it be a 0. So that's what's called an optional parameter. So we're saying, hey, if they don't tell us a balance, we're just going to assume it's 0. So then we always have some comments. Return an account object whose name and starting balance is balance. Whose name is name and starting balance is balance. So what does it do? Notice it says self.name is equal to name. Well, this name and this name are the same. That's the name that we pass in. Here's the customer that we pass in. Here's the balance that we might pass in. This is a different variable here. Self.name is just like when we say turtle dot something, what we're doing is we're saying for this object, in this object, I want this object's name to be the name that they pass in. I want this object, this account's customer name to be the customer name that they passed in. I want this one, this account's balance to be the account balance that they passed in. So notice over here, I say ACL is equal to account, and I pass it checking, bill, and Yakis. And then, I'm sorry, checking, bill, Yakis, and I don't know why. I'm kind of disappointed at that. Let me fix this. No, didn't really want it to, yeah, I like the way that looks better. Okay, so notice that what we're saying is, just like what this is saying is I want to create a new account, call the constructor, and pass it these 3 things. So what this does is it goes over to account and says, well, since it's just the name of the thing, we're going to call the init function. So this calls the init function, and we don't actually pass itself. That's sort of automatic. Don't worry about that right now. So checking goes into name, bill Yakis goes into customer, 1,000 goes into balance, right? And so then what happens is we take checking and put it into this account's name. We take bill Yakis and put it into this account's customer name, and we take 1,000 and put it into this customer's balance. So and then this function returns an account reference, and we're going to call that ACC1. We could call it anything we want. We could call it bill, we could call it A, we call it whatever we want. This is just a variable, just like we can have turtle variables, right? Because turtle is a class. This is an account 1 is Bill Yakis's account. Now we're going to make a second account, savings account for Sue Smith, and we're going to put 2,000 in it, and we're going to call that account 2. Now, what can I do with that? Well, we're not looking at these other things yet. Right now, we're just looking at the basic things. It turns out that I haven't shown you all of it. Okay, wait a second. So then we can do things on it. And here, by the way, we're printing out. Now we're not seeing those functions. We're only seeing the withdraw and deposit. So I'm going to actually click on this, and you can actually play with this on your own as well. Let's go in here and look at this account. Let's look at this code in real life. Okay, so again, notice over here, I have main and account. And let's close that up. And if I look at main for a second, this one's actually has a bit more in there. Let me fork it so I don't change the original one. Okay. So notice I'm making an account called account 1 for Bill Yakis. I'm making an account 2 for Sue Smith, and I'm making account 3 for Cindy Jones, and that's a Christmas account. So over here is everything we saw. I have class account. I have some comments telling me about it. We always want to do that. I say the attributes are the account type, the customer name, the balance. And here is my init function. This is what gets called when I create a new account. This function gets called and it stores in the account those values. Now, what can I do with this? Well, here, this looks like code we've seen before. Here I take account 1 get type. What does that do? Let's look in here. Get type, we have self here, but we don't have to actually pass it anything. Notice there's nothing in here. We're saying for account 1, I want you to get the type. Well, the type, it just returns type. Get balance just returns the balance. Get name just returns the name. So what I'm doing here is when I print, here I'm printing account 1's type, name, and balance. Here I'm printing type account 2's type, name, and balance. And here I'm printing type account 3 type, name, and balance. We call these functions, by the way, accessors. These are just functions that I wrote here that they do nothing more than they pull information out of the object, right? So get balance is going to get the balance for account 1 here. Here it's going to get the balance for account 2. Well, let's run this. So here we see from line 7 through 9, I print out checking Bill Yakis 1,000, savings Sue Smith 2,000, Christmas Cindy Jones, and for Cindy Jones, I didn't pass her a balance when I created her. Notice that. So it just defaulted to 0, as we talked about before. So again, what have we seen so far? We've made 3 accounts, and we've called them account 1, count 2, and count 3. We have printed out the type, name, and balance for each account, and now we want to have some fun. So what we're going to do is we're going to take account 1 and deposit 100. We're going to take account 2 and withdraw 200, and we're going to try to withdraw 2,000 from account 3. Now that might be kind of hard because we haven't put any money in it yet. So let's go back up here and look at our account. So remember, we have the constructor, which is the init. We have 3 accessor functions: get balance, get type, and get name. And then we have a withdraw. And withdraw, we have self amount because we're going to pass it how much we want to withdraw. Well, what does amount do? It says we check the amount to see if it's greater than the balance, because we're not going to let them overdraw. We don't like overdrafts. So if the amount is greater than the balance, it says amount is greater than the available balance, and then it prints the balance. Doesn't do anything then, just prints out that message. Else, we take the balance and we subtract the amount from it, so now this account has less money in it. And then we're going to return the balance. So this function returns the balance if we want it. We don't have to use it, but we can. See what deposit does. What deposit does is pretty obvious. We pass it an amount, it puts it into, it adds it to self balance, and then it returns the new balance. Now we've made a function called print, and print prints the name, and it prints that type. It prints the customer, and it prints the customer's name, and it prints the balance. So let's go up and look at this. Here we do our deposits. Now I'm not actually using the print functions. I'll try to use that later. Let's run this again and see. Well, we can see what happens when we run it. We do our deposit and our withdrawal. When we do our third withdrawal, it says amount 2,000 is greater than the available balance, which is 2.0. And then I reprint these, and notice Bill Yakis now has 1,100. Sue Smith now has 1,800 because we took $200 out. And of course, Cindy Jones is still at 0. So she needs to get her act together. Now, notice that over here we had a print. Why don't we use that instead? Well, it turns out we can. I can take all this code out and I can just do an account1.print since I wrote that. Oftentimes we want to do that. That's a nice little shortcut of account2.print and account3.print, right? And I can actually take that same thing and put it down here. That makes it a lot simpler. Look at how nice that is.